Wizard. So today we're going to talk about characterization of functions in H1. Right? So we're talking about party space, right? This is a replacement for L1 in analysis. And you recall how we define party space, right? So you define H1R, party space, in sort of a funny way. We said we're going to define it to be all functions in L1, so to be defined H1 to be all L1 functions, such that something happened, right? All L1 functions F, such that F has an atomic, F has a kind of particular decomposition, right? So do people remember the qualities of this decomposition? Right? You're going to, right, F can be written as some sum of some combination of these guys called atoms, right? And the atoms have to satisfy where when the AK are atoms. And what would it mean to be an atom? What's an atom? Satisfies these two conditions. Needs to be what? Small, right? Size condition and a cancellation condition, right? In other words, right, we wanted the L infinity norm. Well, sorry. So first thing is that the support, each of the atoms is supported on some ball. Support of the guy is in some ball. Right? We needed the size condition, right, that the L infinity norm was controlled by 1 over the measure of the ball. Right? So that when you integrate it, so that the L1 norm is 1, right? It's controlled by 1. And the third thing was the cancellation condition, right? That you wanted the integral to be 0, right? Right. So where these guys are atoms, and then the second thing was that you wanted the sum of the coefficients, the little L1 norm of the coefficients was finite. This thing was finite. Right? And so any L1 function that was like this we said was in H1. And we made some comments about it, that if you're in H1, then it forces you to be to have integral 0. I guess that's maybe pretty straightforward. And other we made some other comments. So the thing we're going to go for today is sort of the opposite of that. The statement about the cancellation, that any function, so composition, if F is in LP, and F has bounded support, then, so under those conditions, F is in H1R, if and only if it satisfies the cancellation condition. So the interesting part of this group is the backwards direction, and so to do this, we'll use the famous Calderon-Zygmund decomposition, which turned out to be the great one of the great tools in analysis for some 30 or 40 or 50 years. I'd say even now, people use variants of the Calderon-Zygmund decomposition to understand things. So, like I said earlier, when my postdoc advisor asked me, what result would I put my name, would I plagiarize if I had the chance to wipe somebody's name off and put my name on it? I chose the Calderon-Zygmund, the O decomposition. Yeah, the Calderon-Zygmund decomposition. So yeah, it wasn't, it wasn't really clear that this was the thing to do, but it really is the thing to do in analysis. This decomposition. Does anyone have a sense of the decomposition if you've read the material? Would anyone like to say what your impression of, like, what's the idea of it? You have this function, you have some height, you do a Calderon decomposition at a certain height. What does that involve? Or what's the idea? Anyone have a sense of it? It's okay if you don't. We'll talk about it. So, roughly speaking, it involves taking the function and decomposing it into these two other functions, right? And G and B used to mean were initially meant good and bad. Okay, so the good, you decompose it into the good part and the bad part. Okay, and the good part is good in the sense that it's small. It's small in some sense. Okay, and for us. In this context, small will mean L infinity small. Okay, so we're going to decompose in some height alpha, and G will have the property that it's bounded. Its L infinity norm is controlled by alpha. Okay. Now B is the bad part. So it lives on the place where it's. Okay, so really what one does is one takes the support of f and then divides it into two pieces using a maximal function. Okay, so you consider a maximal function, some sort of maximal function of your function, and you consider the set where the maximal function is big. Okay, so the B is going to live where the maximal function is big. The G this is not exactly right, but G, the important part of, anyway, so let me just say that the B lives where the maximal function is big. Okay. And what one does is breaks this set up into disjoint portions, and then on each portion, on each ball, basically, on each ball, you adjust the function so that it has zero norm over and the integral 0 over that ball. Okay, so you take your function and you break it into these two parts. This part is going to be small in some sense. This part is not small, but it has the nice property that it's further broken up into these smaller guys, each of which lives on a ball and has integral 0. Okay, so there's sort of like a forerunner of an atom. Okay, sort of like a forerunner of an atom, and in this proof we'll do sort of an iterated thing that will result in the atomic. We'll show that these guys have an atomic decomposition. Okay, so so there are a couple ideas. One is that it's a good idea to break the function into these two bits. One where the function is small, and two where the function is further broken down into these guys who satisfy cancellation. Okay, so it turns out that in the world of singular integrals, you can control your behavior on the good guy using some LP bound, and then you control your behavior on the bad guys by using the smoothness of the kernel that you're convolving against. Okay, so that turns out to be like the key, a big key to getting results. Okay, so so I was pretty excited to be talking about the Calderon-Zygmund decomposition. I woke up at 4 a.m. this morning out of excitement. Now I'm tired. Now I'm tired, but I have to do it some justice. Okay, so so here we go. Let's show that if your function is an LP and has bounded support and its cancellation is 0, then it has the atomic decomposition. It has an H1R atomic decomposition. Okay, so without loss of generality, let's assume F, the support of F is contained in some ball of unit radius called V1, a ball of radius 1. And let's also assume that the L1 norm of F is less than 1. Okay, so now the maximal function we're going to use is this this thing that sign denotes F super dagger. Okay, he calls it the truncated. So we define the truncated maximal function of F by taking the supremum. It's just like you did before. You take the average of the absolute value of the function, okay, over all balls containing your point. Okay, but you place the restriction that where the radius of the ball is less than or equal to 1. Okay, so you don't take supremums too far. You don't take averages too far away. You just at most you take things one unit away or half a unit away. Okay, let's first make the observation. So first observe. First observe that if F is an LP, then F dagger is in L1. And the reason is that if you consider the L1 norm of F, well, the L1 norm of F dagger, well, so this is for our F. I should say this, since our F is in L1, our F dagger, since our F is in LP, F dagger is going to be in L1. And the reason is, notice that the support of F dagger is the concentric triple of B1, right? Because F is supported on B1, some ball. Right? The support of F is inside this ball. F dagger takes averages only over balls of radius 1. Right? So by the time if you're outside of B3, and you're looking at F dagger, well, you're taking averages of 0. Right? So the support of F dagger, is contained in the concentric triple of B1. Okay. So we know that this is the same thing as the integral over B3, right? And then you apply Hölder's inequality to this, right? You see that right, you can say this is the same thing as B3 F dagger over RB. Right? By Hölder's inequality, you get the measure of B3 to 1 over B prime, and then the LP norm, right? The LP norm of F dagger, right? You get the LP prime norm of chi sub B3, right? Times the LP norm of F dagger by Hölder's inequality. And you know that well, what's the relation between F dagger and F star? the old maximal function, f star, you're taking the supremum over all balls containing it, so it's going to get bigger, right? So we know that this thing is, that this integral is finite, right? Because f was an LP, and f star is an LP also, right? Because the maximal, highly limited maximal function is bounded on LP, right? So this thing here is bounded by the LP norm of the highly limited maximal function. Okay. So this whole thing is fine. Okay. So that shows us that f dagger is irrelevant. Looking at this integral, we know that it's bounded by this, and we know this is finite because this is because the party little maximal function is bounded on LP. Okay, so that's just our initial. All we're doing at this point is introducing the relevant maximal function. Okay, the relevant maximal function is going to be this f dagger guy, sort of local averages locally, takes the supremum of local averages. Okay. Okay. So now we are going to use the. Now we're going to do the Calderon-Zygmund decomposition. So here we go. So here's what we do. You fix a value alpha. Okay. Fix some value alpha, and you let E sub alpha, as we said before, be the set where the maximal function exceeds alpha. Okay. Okay. And for now, a remark. For now, let B be equal to 1. Okay. And the reason for this is that if you're talking about, this is an open set. E alpha is an open set. And what we're going to use is the fact that in R1, if you have an open set, well, it can be decomposed into a disjoint union of open integrals, right? Okay. But in R2, what do you do? If you have an open set, is it decomposable into a disjoint union of balls? Well, no. Right? Not so simple. Okay, so in R2, for dimensions above 1 needs some sort of replacement for this decomposition. And that's something called, we'll use something called the Whitney decomposition. So there is like a higher dimensional analog of this statement, or not an analog, not a true analog, but a replacement, a tool that we can use to replace this one-dimensional thing. But we need to create that tool. Okay. Okay. But for now, suppose that we're in R1, so that we can use this fact that any open set is decomposable into a union of disjoint open sets, open integrals. Excuse me. Okay. So. The alpha is decomposable as a disjoint union of integrals ij, where the ij are open integrals. Okay. So just to use a notation that I haven't used in a while, this is the disjoint union. It's like this. So I gotta just say this. These guys are disjoint. Okay. Okay. So here's what we do. Like I said, we decompose F into good and bad. And Stein doesn't call them good and bad in his book. I assume this is because the bad is actually not that bad, if you think about it. Bad actually turns out to be pretty good. The good is good. There's nothing, it's not actually bad. But the bad actually is pretty good. Okay. So maybe that's why he doesn't mention it. Okay. So so what are good and bad, guys? So let's define bad first. So for each interval, S of j, we let b sub j be f minus f sub j I sub j, where m sub j is the average value of the function f over that interval. So on every, you take this set where the maximal function is large, you decompose it into its open intervals, right? And then on each open interval, you take the average of the function. Okay? You take the average, the actual average, not the average of the opposite line, but the actual average, and you subtract off. You define a function to be it's going to be f restricted to that interval, but with the mean subtracted off, so it has mean 0. Okay. Okay. And we let them be the sum of bj's. Okay. Okay. Of course, the supported mean is b alpha, and the mean of b, the average of the interval b satisfies the cancellation condition because each of these guys satisfies the cancellation condition. Okay. Okay. So then we let the good part. Once we know the bad part, we know the good part, right? Because they sum to f. Right. So then g is going to be f minus b. In other words, g is going to be f times the characteristic function of the complement of p sub alpha, plus all those things that you subtracted off. Right? So it equals f on the complement of e alpha, and on e alpha itself, it takes those average values. Okay, on each of the intervals, it takes those average values. Okay. Okay. And let's see. What's here? So make a couple of observations about G. Right. Is everyone okay so far? Right. How we define the good guy, good part, and the bad part? Okay. So observe. So observations about G. First off, for x in the complement of E alpha, we know that f dagger is less than alpha. It's less than or equal to alpha, right? Just by definition, right? E alpha is where f is bigger than alpha. E alpha complement is where you're less than or equal to alpha, of course, right? Okay. This actually forces f to be less than or equal to alpha almost everywhere. This is true by something called the Lebesgue differentiation theorem. but maybe you can sort of believe it if you think about what this means, right? What this means is that every average, if you have a point x and you're taking averages over balls less than size 1, over intervals of less than size 1, that average is always less than alpha, right? So over every average, as those balls shrink to 0, all the averages of the function are less than alpha, right? The supremum of those averages is alpha. Right? So this is less than equal to alpha. And at least for continuous functions, it's obvious that this is true, and then you can argue from there to get the LP functions. So there's this theorem called the Lebesgue differentiation theorem that makes this rigorous and tells you at what kinds of points this happens. At what kinds of points it is less than or equal to alpha. Okay. So that's our first observation that that G is less than or equal to alpha outside there. Right? I mean F. And of course G. Right? F is G. The second observation is that for if we consider the a single interval in one of those open intervals, then we have that the average of the function in absolute value is less than or equal to alpha. Okay, so this m, what we call m sub j, we know that the average is less than or equal to alpha. And the reason is that you break it into two parts. If the measure of the interval is greater than 1, then it's clear. Right? If it's greater than 1, then you have that this is this is great. Then it's immediately clear, right? Because you're dividing by something bigger than 1, right? So this is smaller than the integral, right? Okay. This number is smaller than 1, right? And this is smaller than the L1 norm of f, which is smaller than 1, and we assume that alpha was bigger than 1. Right? So this is for intervals that are big, this is immediately true. If the interval is bigger than 1, right, then when you divide by the length, you're multiplying by some number that's smaller than 1, and so you can just get rid of that number, right? Which means that the average is controlled by the L1 norm, right? The L1 norm by assumption, right? We assumed that the L1 norm was less than or equal to 1, and our alpha was bigger than 1. So that makes this true. Okay, and then and then the second part, if the interval is of length less than 1, then say I equals x1, x2. Suppose the interval looks like x1, x2. Then x1 is in the complement d alpha c. is in the complement of E alpha. But that means that f dagger x1 is less than or equal to alpha, right? But f dagger controls the integral over, controls the average over ij of the function. Right? And so that tells you that in either case, this average is controlled by alpha. Okay. So what does that tell you? So altogether, one observes that the good part is smaller than alpha. Almost everything. Okay. Right. Because off of where the maximal function is small, the function is small. Right? The maximal function being small there, by differentiation, shows that the function is small there. Right? Where the maximal function is large, right? Where the maximal function is large, f is equal to the average of the function. F is equal to the average of the function over that interval, right? But we see what happens is when we consider this, the average of the absolute values of those guys, each of those averages is bounded by alpha. Okay, so those averages are bounded by alpha, and so the function is bounded. I feel like I'm losing people. Am I losing people? Are you guys lost? No? Okay, good. Are you bored? Are they lost or bored? Or as usual? I don't know. Okay. So, in any case, we have the main things that we need. Okay. We've decomposed f into G and B. Okay. G turns out to be small, right? G is small, and B is further decomposable into pieces, each supported on those intervals, such that the integral on each interval is 0. Okay. So those are the properties that we're going to need. Okay. So that's the Calderon-Zygmund decomposition, breaking the function into these two pieces, the good and the bad, where the good has some size condition, satisfies some size condition, and the bad satisfies some cancellation condition. Well, it can be broken down into pieces that satisfy cancellation condition. Okay. So now we're going to try to get the atomic decomposition of the function whose integral is 0. Okay. We have this function, it's in L1, in LP, it has bounded support. We know it satisfies cancellation. Let's show that it satisfies the atomic decomposition. Or it has an atomic decomposition. Okay. So constructing the atomic decomposition of F via a Calderon-Zygmund decomposition at all scales. I should say via simultaneous Calderon decompositions at all scales. Okay. So we take alpha to be 2 to the k. So previously we decomposed at height alpha. Now we're going to take alpha to be, we're going to take a lot of alphas. Okay, so alpha will be 2 to the k, where k is 0, 1, 2, 3, etc. Okay. and we'll do a Calderon decomposition at each height. Okay. So we decompose F as G super K plus B super K. Okay. Where these K's are not powers, but just an index. Okay. So we Calderon-Zygmund decompose F into these things. Decompose F at height 2 to the K. Right? At each height, we get some decomposition. F breaks into these two parts. Okay. So G is, of course, supported where the maximal function exceeds 2 to the K. No, sorry. B sub K is supported where the maximal function exceeds 2 to the K. And G is supported everywhere, but equals the function on the complement of that set, and equals the averages on that set. Okay, so just notation, right? Notate e sub 2 to the K as, so we need that, we're going to need that decomposition, right? E to the K is as before, right? Where F dagger exceeds 2 to the K. And it's an open set, and again, we break it down into intervals, right? So the K indicates the scale. The K indicates the scale, and the J is the index. Right? So the union over all J gives you the setback. Okay. So, and we notice that, note also that G super K is bounded by 2 to the K, as we saw before. It's bounded by alpha, right? And we also have that B super K is further broken down into its constituent parts, where, so maybe I should write this up here. So G is bounded by alpha, and B is further decomposable into these guys where the support of BJK is contained in IJK. And the integral of BJK is 0. Okay. So, in other words, we do a Calderon-Zygmund decomposition at all scales. Okay. So now comes the cool part. Observe that, like we just said, F is G plus B, and we know that the support of BK, right, is contained in B sub 2K, right, by construction. Now, if we think about E sub 2K, right, E sub 2K is where the truncated maximal function is bigger than alpha, right? And so that's contained in the set where the star maximal function is bigger than alpha. Right? Because certainly if the truncated guy is bigger than alpha, the full guys can be bigger than alpha. Right? Okay. And what do you know about this? what do we know about this size? We know that the size of this thing is, we know that the size of this thing goes to 0, right? Goes to 0, sorry, this alpha should be 2 to the kings. Okay. We know that, for example, I need to do this a couple ways, but we know that, I mean, you can either say f is in LP, and m, the maximal function is bounded on LP, and so you end up with this weak inequality, right? Or you can say that this guy is in, the function is going to be in L1, and you can use the weak 1-1 inequality. So either way, however you do it, you see that as alpha, as k gets large, then this thing goes to, the size of the set goes to 0. Right? So we see the measure of u2k is bounded by this, and so, right? So the measure of u2k goes to 0, right? But that tells us that G super k converges to f pointwise, AE, right? Because this guy's support goes to 0, so it's going to be 0, you know, it's going to be 0 almost everywhere it will go to 0. Okay. So that tells us that thus f equals the limit as k goes to infinity of the G sub k is almost everywhere. So I'm going to need a lot of space for what comes next, so I'm going to back up. Okay. Now comes the really cool thing. So we're going to write f as a telescoping sequence. D super k minus dk. K goes from 0 to infinity. So we write this f as a telescoping sequence. Right? This is true. True almost everywhere. So we write f as a telescoping sequence. And we say, okay, right? But we can write this as b sub k, b super k minus b super k plus 1. Right? Because it's g super k plus 1 plus b super k plus 1 equals g super k plus b super k. Right? And just switch the signs. Bring this guy over here, bring this guy over there. Right? The difference of the g's equals minus the difference of the b's. Okay, so that's good. Right? We're starting to see maybe some inklings of the atomic decomposition, right? Because these guys are all expressible in terms of those sub guys who are each have integral 0, who all satisfy the cancellation. Okay, so let's go further, right? Let's further break these things down. So we get b super k is expressible as the sum of the b sub j super k's, bj k's. Right? And this guy is a different index, b sub I super k plus 1. guys aren't smiling, but that's okay. I'm smiling. It's enjoyable to me. It's for me. This is sort of like seeing an old friend or something. Okay, so or an old enemy. What are you? Okay. So observe. We make the following simple observation that e sub 2 to the k contains e sub 2 to the k plus 1, right? Because if the function is bigger than that, so it means bigger than 2 to the k, right? That tells us that if we look at the decomposition into intervals, right? These guys, the union of these intervals, right, is contained in the union of these intervals. Right? Each one, right? Each of these intervals, each of these k plus 1 class intervals, right? From each of these guys from the higher value is going to be part of e sub 2 to the k, right? And in fact, is going to be contained in only one of these, will be contained in only one of the I sub j to the k. Right? So observe each guy from the higher class, right, satisfying the harder condition, is contained in a single guy from the lower class. Right? You take your e sub 2k and you broke it down into its intervals. Right? If you think about it, I think it's clear. Okay. So we use that fact to rewrite this statement here. So let's rewrite this. Let's just simplify this a little bit. We'll write this as summation over j djk minus. So for you fix each interval in the lower class. Fix each interval in the lower class and subtract off from it all of the b I p plus 1, where this interval lies inside I sub j. Okay. So we're going to subtract off all the over all where I is such that this interval lies inside of that interval. Okay, and that will give us, in the end, that will give us all of these guys. So we're just partitioning them. Instead of subtracting them all at once, we're going to subtract for each fixed ijk. For each fixed ijk, we're going to subtract off the guys who live inside us. Okay, the guys at the next higher stage whose intervals live inside of ijk. Okay. And that will give us all. Okay. Okay, does that make sense? Okay, and we're going to call these guys, we're going to call this thing A sub j k. A sub j k. So A sub j k is going to be the bad part living on ijk minus the bad parts that are living on all I sub I k plus 1 that are inside ijk. Okay, so now let's observe. Are you guys really okay? I don't know. Is everyone all right? Do you have questions? Any questions on where we're going, or any questions on what things are? Okay, remember what we're doing. We're trying to make this guy. We're trying to give it an atomic decomposition of this guy. We're basically not. We're almost there, right? We used. How do we get the atomic decomposition? We do this Calderon-Zygmund decomposition at all scales. Right? So we take F is G naught plus B naught, G1 plus B1, blah, blah. We realize that F can be expressed as as the limit of the G's. As the limit of the G's, use a telescoping sequence to get to this as a difference of the difference, a sum of the limits of the B's. And now we've partitioned certain parts of the B's into pieces. And these pieces are going to basically be our atoms. Okay, so here we go. First off, observe that, well, this first one is obvious. The support of AJK is IJK. Right? Because each of these guys lives inside IJK. This guy lives on IJK, so it just lives on, the whole thing lives on IJK. Okay. And so for fixed K, these guys live on disjoint intervals. Right? So for fixed K, the AJK live on disjoint intervals. Okay. The second thing to notice is that if we take the sum of the, if we take the sum of the if we take this sum here, right, then we get this. Right? So the sum of the AJKs equals G for fixed K equals the difference of the G of the good functions at those different scales. Right? And for fixed X, only one of the AJK is non-zero. Right? Because they live on disjoint intervals. Right? They live on disjoint intervals, so if you evaluate it at some point, well, all of them except for one, at most, is going to be non-zero. Right? So what that tells you is that if we look at the absolute value of AJK at some point, well, that's actually going to be this, the difference of the good functions at that point. And then we know that this in size is controlled by alpha. This is controlled by alpha. Right? This is controlled by alpha. It's its own alpha. So 3 times 2. Okay. So we have we have this control on the size of the AJKs. And the third observation is that the integral of the AJKs is 0. Okay? Because each of them is composed of things whose integral is 0. Okay. Okay. So do I have enough space to do this? So now here comes the atomic decomposition. So let let fancy A JK equal 1 over n, the measure of IJK, 3 times 2k AJK. So we just take our old AJKs and we multiply them by some constants. Okay. And let lambda JK be the constant, be that constant when we just divide it. So that F then is equal to G naught plus summation JK fancy A J. Okay, and so what we need to see, okay, so the only thing we need to do is check that we need to check that these guys are atoms, right? So are they atoms? Okay. Well, we know that the AJKs live on IJK, right? They live on IJK, and we know that if we take the absolute value of this thing, right? We just saw that this size of this is controlled by 3 times 2 to the k, right? So the absolute value is controlled by 1 over the measure. So it satisfies the size condition, right? And the integral is 0, so it satisfies the cancellation condition. So these guys are atoms. We needed to throw in this constant to ensure that it is an atom. So these guys are atoms. What we need to do is to show that that the sum of these things is finite. So that's the last, basically the last serious bit. Okay. So right. So observe that. We just saw that this was controlled by 3 times 2k, so, and that satisfies the cancellation, and so that forces a fancy A JK is that. Right. And sorry. So we need to check the condition on the coefficients that summation lambda jk is finite. Okay, so here we go. Well, if we take the sum k, j, lambda. These guys are all positive. summation k to k summation m I j k. Okay, and when we add up, if we sum up over all j's, well then we get e sub 2k. Right? Okay, so we get 3 summation k to the k times the measure of e sub 2k. Right? In other words, the set where a dagger exceeds 2k. Okay. Now, this function, if we look at this distribution function, so notice that this is a decreasing function. Right? This is a decreasing function. As a gets bigger, then this thing gets smaller. Right? Right? So, so what does that tell us? That tells us that so if alpha is less than 2k, then of course the measure of the set is smaller than the measure of this set. Right? For any alpha, the value is just going to get bigger. For any smaller alpha, the value will just get bigger. Right. So what that allows us to do is to replace this by an average. Okay. So we say, okay, we're going to average. We're going to average that. We're going to average. We're going to average this thing over the interval that stops at 2k. Okay. So we're going to average the distribution function over the interval that ends at 2k. Right. So it's only going to get bigger. Right. This will give us something bigger. We need to average it, so we divide by the length of the interval. Right? Okay. In other words, we get summation k integral 2 to the k minus 1k and 2 to the k and this is great, right? You see what's happening. We have simply recovered the L1 norm of f dagger, right? So this gives us 6 times the L1 norm of f dagger. Right? But we saw earlier that that's fine. Right? The L1 norm was controlled by some constant times the LP norm of f. That constant arising from the LP boundedness of the Hardy-Littlewood maximal function. Okay. So that's it. Right? We found that the coefficients are the sum of the coefficients is finite. So there's only one thing that's not done, and it's trivial. So only one thing is left. Only one thing is left. G naught. Right? There's that guy G naught. So we do have to deal with G naught, but it's easy. Right? G naught is bounded and supported in V3. Right? G naught is bounded by 2. Right? By 2 and supported in V3. Right? And here's the funny part. The integral of G naught is 0. Why is the integral of G naught 0? Why is the integral 0? Well, because the integral of f was 0. Right? And the integral of these guys is 0. Right? So when you take the difference, and this is maybe the only place where we use this fact, that the integral of f is 0. It's so humorous. So this is where we use that fact. The integral of f satisfied the cancellation. That was part of the assumption of the theorem. This guy we just showed these guys are all atoms, so the cancellation is 0, and that gives us that the integral of this guy is 0. Well then, if you multiply g by some appropriate number, right, then g is an atom itself. So G naught is some multiple of an atom. Some multiple of an atom itself, and that's the end. So you have F is expressible as a sum of atoms where the coefficients sum where the sum of the absolute values of the coefficients is finite. 2 minutes left in class. So I finished a little bit early. Should have started the Any questions? I hope you think this is great, because it really is great. It's just magnificent. You get the atomic decomposition by taking Calderon-Zygmund decomposition at all scales simultaneously, and then recognizing that the GK converges to F, and that allows you to express F as the sum of differences of the pieces of the band parts, which you can toggle to become atoms to give you the atomic decomposition. I only met Calderon once. He was at the University of Chicago. He's like one of the kings of the University of Chicago. Right? But he is long retired since when I got there. He came to tea one time, and I just said, I think I'm spending my whole life studying your work. And he's like, Yeah, one of the great heroes of mathematics. Okay, that's it. Goodbye.